Hello, good evening. So I'm just waiting for some more people to join. So I think we can get started in 2 3 minutes. So I think we will just wait for 1 more minute and then we can start. Okay, I think so then we can start now. Uh, so so welcome and thanks for joining this session. My name is Parth Joshi. I am basically I am a PhD student in the Department of Mechanical Engineering at IIT Bombay, and so I have been conducting these online problem solving sessions since the last 4 weeks, and this is the fifth session. So in every week, basically, I am covering the problems which are similar to the problems which you will find in the assignments, and these sessions are basically intended to for you to basically to clear whatever your doubts and help you to understand the concepts related to that week's content better, and also to help you in getting some idea of how to solve the problems which are similar to the assignment problems for that week's assignment. So hopefully this session will also be helpful for you. So I have been basically conducting these sessions as a part of Prime Minister's Research Fellowship. And so I have been given a chance by the NPTEL team to conduct these sessions. So uh, and I have been basically recording all these sessions and uploading them, and so I think all of you are able to access the recordings and the lecture slides for the earlier sessions.
Yes, sir.
Okay, fine. So so Shrivalli, so Yeah, thanks for joining this session. So, have you joined the earlier some of the sessions?
I have, sir,
Okay,
mm, just for some amount of time.
okay, fine. So, are you like a student or you are a working professional or who is it?
Student, sir,
Okay, so
third year
where,
student,
sorry, third year student.
third year engineering student,
Okay, which branch of engineering are you studying?
aerospace.
Aerospace. Okay, fine. Okay. So, like, because this course is actually applicable to any engineering branch as such, but the particular concepts which are like some of the concepts you may be familiar, some of them you may not be. So accordingly, so I need to you know, either describe, or if you are already familiar, then I can just go ahead and skip that part. So anyway, so yeah, so I think before we begin, so do you have any questions or comments uh, related to either
No, sir.
content of this week
Mm,
or previous week?
No, sir.
Okay, fine. So I think we can get started. So I am sharing my screen now. So I am right now sharing my screen. So are you able to see my screen?
Yes, sir.
Oh, sure. Thanks. So the content which is for covered for the lectures in this week is basically dynamic response of first order and second order systems, and then there are some performance measures that are defined for second order systems, and the concepts related to transfer functions, basically transforming the uh, basically getting an algebraic relation between the input output, and how do we get that transfer function is through using the concept of Laplace transforms. So that has been covered, and so I think if you are a third year engineering student, or even like if like something more than more senior than that, I think you should have covered the concept of Laplace transforms in your engineering, right?
Yes, sir.
Yeah. So so this concept of transfer functions, was it covered for you in your engineering earlier subjects?
Just basic theories,
Okay.
not very much.
Okay. Fine. Fine. So basically this concept we will be using for deriving the transfer functions, like using Laplace transforms. So we will be looking at some problems related to each of these concepts that have been listed here, and hopefully those problems should help you in solving some of the assignment problems. So any questions, comments?
No, sir.
Okay. So then we can just start with the problems. So I have basically from my side, I have made a list of some problems. But if you have any problems of your own which you want me to discuss or something like that, so just let me know that also. So I am just sharing my screen now. Yeah. So let us start with our first problem. the transfer function for a first order system under a unit step input is given. So that is our transfer function. So we have to calculate the time period at which the response can reach 63.2% of its total change. So any idea how we solve this kind of a problem?
No, sir, I need help.
Sorry?
No, sir, I don't know. I haven't watched last two videos yet.
Okay, fine. So basically uh, this is the transfer function for a first order system, and the general transfer function for a first order system we can write it as 1 upon tau s plus 1. So where tau is our time constant. So and the time constant is basically the time required to reach 63.2% of its steady state value. So let us say if we apply a step step input, and and then I'm drawing the system's response. So the system starts again at 0 at this point, and then it will steadily rise to the steady state value. So if this is 1, and so the value of the time at which we reach this 63.2% of the steady state value, so that is called time constant. So if we compare this with the transfer function for our problem, so we can say that tau is equal to 5. So in 5 seconds the response of the system will reach to 63.2% of its steady state value. So if we want to write down what is the inverse Laplace transform for this, so then we can say that so the step response will be basically for a unit step input. So the response, let us say if we apply a step input, so then it will be uh, the Laplace transform of a unit step input starting at t equal to 0 is 1 upon s, and we want to find out what is the response xs. So basically xs by ys is our transfer function g of s. So we can find out the inverse Laplace transform for this by using this concept of partial fractions. So what we can do is we can say that x of s is g of s into y of s, so which is 1 upon s into 5s plus 1, and so basically we can write this as so basically we have to write this as in terms of a upon of the form a upon s plus something b upon 5s plus 1. So uh, so how do we write this is basically using this concept of partial fractions, and then we can just take simply the inverse Laplace transforms of these individual uh, a by s and b by 5s plus 1, those terms, and then we can get the inverse Laplace transform for the overall system's response. So now how do we find out that is by uh, comparing the coefficients of the numerator and denominator. So the so basically we have that uh, 1 upon s into 5s plus 1 is equal to a upon s plus b upon 5s plus 1. So if we compare the coefficients of the numerator and denominator now, so if we so we can equivalently we can write this as a into 5s plus 1 plus bs upon s into 5s plus 1. So we can compare the coefficients of the numerator and denominator now. So what we will get is that so the coefficient of the so the numerator is 1 for this left hand side, and so we have a 5a plus b as the coefficient of s and a. So now this is on the left hand side, we do not have any term of s, so then we can say that 5a plus b is identically 0 and a is equal to 1. So therefore b is equal to minus 5a, so equal to 5 minus 5. So basically we will get, so it will be 1 upon s plus, since b is minus 5, so we will write it as minus 5 upon 5 s plus 1. So the 5s plus 1 we can write it as so 1 upon s minus 1 upon s plus 1 by 5, so which is basically, so the inverse Laplace transform for this will be basically 1 minus e to the power minus t by 5. So this will be our response. So this is how we can get the response for this first order system. So any questions?
No, sir.
Okay. Now this is a similar problem. Now can you tell me what will be the time constant now for this particular case? If we apply the same concept here now.
144 by 7.
144 by 7. Okay, how do you get that?
Sir, numerator should be 1. So we divide the entire thing by 7,
Mm-hmm.
numerator, denominator. And the 9s plus 16. 16 also should be 1. So we multiply, divide by 16.
Uh, so the numerator should should be one that is actually not a problem basically. So that is just that's like a gain term. So that will just increase it's a just a simple multiplying factor. What is more important is the coefficient of s. That the denominator is more important. So it can be something of the form a upon some tau s plus 1. So in that this coefficient tau is the important thing. So if we now divide the denominator and numerator both by 16, so then we will get 7 by 16 into 1 upon 9 by 16 s plus 1, right? So now we have, so whatever in the curly brackets part, so this is in that form of uh, 1 upon tau s plus 1. So then we can say that tau is basically 9 by 16. So that will be our time constant in this case. So that will come out to be 9 by 16 will be 0.5625. So that is how we can get the time constant for this particular case. So the term 7 by 16 is just like a amplifying kind of factor. So that does not really change the time constant. Is that okay?
Okay, sir.
Now, so we have been in this question, we have been given a second order differential equation. So now it is asked like what is the damping ratio and the nature of the system. So what will how do we solve this problem now? How do we find out the damping ratio and the what is the nature of the system?
So we find under the root tau square minus 1, what is the value we get?
Okay, okay,
So if it is more than 1, then it's over damped, equal to 1, critically damped, less than 1, under damped.
okay. So but how do we find out that factor, damping factor, damping ratio?
Uh, Damping ratio is given by root of c by 4 mk, c square 4 mk.
Okay. So what is MCK over here?
C is 25.
Okay, fine. So C is 25. Okay. Then,
M is 5.
right. Okay. M is 5.
K is 100.
Okay, fine. So then, uh, whatever by the logic that you are saying, so we will get basically the zeta or whatever that damping ratio what we call. So that is C square by 4 mk square root. So that's what you are saying, right?
Yes, sir.
Okay, fine. So we'll try that. So it's basically C by 2 root mk. So it's basically 25 by 2 into. So it's basically 25 by 20 into root 5. So it's about 0.559.
Yes, sir.
So it's about 0.56, right? So now
Yes, sir.
say, so now what we can say further?
Since it's less than 1, no, it's underdamped.
Yes. So it is underdamped. Yes, you are right. So this is the correct answer. So it's a second order differential equation. So the value of the damping ratio is 0.56 and the system is underdamped. So the way you compare the coefficients, so we can also do it this way. So we can divide the entire differential equation by 5. So then we will get the differential equation like this. So x double dot. So I'm writing it in a shorter form so that for the space part. So and so the usual equation for a second order system, we can write it like this. Now we can compare the coefficients in this way also. So the way we did it for C, M and K, so we can also do it directly for zeta and omega n in this way. So this way also we can get the same answer by calculating. So the coefficients of like basically the omega n square will be 20 and then 2 zeta omega n will be 5. So using that we can get to the same answer. Make sense?
Yes, sir.
Okay. Okay. Fine. So now we have a torsional system. So it's given that there is a shaft which has a disc on it, and the torsional stiffness of the shaft is given, and the polar moment of inertia of the disc is also given. So then we have to find out what is the natural frequency of the system. So how can we calculate that?
Don't know, sir.
Don't know. Okay, fine. So we have been given the polar mass moment of inertia. So let us call that as J. So J is given by 125 kg meter square. So that is the polar moment of inertia. And the torsional stiffness is given to be something K. So it is 785 600 something Newton meter per radian. So what we basically have to find out what is the differential equation for this system. So it will be, so the torque acting on the disc because of the twisting of the shaft will be basically J theta double dot. And since we are given that the torsional stiffness is K, so the torque which is uh, applied by the shaft onto the disc, so it will be basically the uh, opposite to uh, the actually the torque that is um, so basically, so it will be opposite to the angular displacement. So that, so if we displace it clockwise, then the torque acting will be anti-clockwise. So then that's why it's minus theta. So then we get this kind of a second order ordinary differential equation. So we can rearrange it to write it in this form. And we can compare it with the standard form for a, let us say, a single degree of freedom undamped system where damping is not present. So by comparing the coefficients, we can say that omega n square, which is the natural frequency, so that is basically k by j. So this, so this is in radian per second. So for hertz, we need to divide it by 2 pi. So let us call that as Fn. So it will be 1 by 2 pi root of k by j. So can you try to calculate now what is the frequency now with this?
$12.62 hertz.
Okay. So let me just check. Yes, so I get about 12.617 something. So which is, so you're right. So it's 12.62. So let us move to our next problem now. Which of the following statements are true? Uh, Maximum percentage of overshoot directly indicates the relative stability of the system. Decrement is the ratio of first overshoot to second overshoot. As the damping ratio increases, the percentage of overshoot decreases. Number of oscillations are independent of the damping ratio. So now which of these statements are correct?
Sir, what is overshoot?
Okay, so overshoot is basically the so the tendency of the system to uh, like go beyond what is the steady state value. So if, for example, if you like, if you can uh, imagine like let us say there is a spring mass kind of a system, and if we apply some constant force, like if we just suddenly like pull that like spring mass damper kind of system, so in that if we just pull the mass and just hold it with a constant force, then uh, because of the kinetic energy that the mass will acquire, uh, then that will be uh, causing the mass to kind of go beyond the whatever static deflection because of that constant force. So then that is basically the what is called as the overshoot value. And if there is damping present in the system, then the uh, the mass will eventually return to that steady state position, which corresponds to that, let us say, some static deflection because of a constant force. So that corresponds to the step kind of a response. So graphically what it means is that, so if we, let us say, apply a step kind of an input, then I'm drawing the response now in blue color. So let us say the system starts from 0 at time t equal to 0. So this is time, and this is, let us say, x versus time. And so initially as the step input is applied, the system will tend to rise, and then it will go beyond the steady state value. And now if there is some damping present in the system, then there will be some oscillations, but it will oscillate about this equilibrium position, and then eventually it will come close to this steady state value. So the extent by which uh, the response goes over the steady state value, so that is the first, like let us say, maximum overshoot or peak overshoot. Then decrement, uh, so that is whether it is the ratio of first overshoot to second, or what is that correct? So that for that we need to know what is the definition of decrement. So I think some of us have joined right now. So I can see Mr. Kamlakar and Venkat. So yeah, thanks for joining. So I have started with some problems related to, yeah, good evening. So I
Good
have,
evening, sir.
yeah, good evening. So I have started with some of the problems related to the content for this week. So till now we have completed, I think, four problems, and this is the fifth one. So I hope both of you, like all of you, stay to the end of this session. Uh, so for those who joined late, so do you have any questions or comments related to the content for this week? So
Sir, I have a question.
yeah,
Uh, we have a live session for this course this year. Did you have a live session last year also for this course?
no, not me. It was not me.
Will it be possible to share the details of last year's session? Because the questions given in the assignment are little and they requires good amount of knowledge to solve. So, if you can kindly share who has presented the last year session, it will be helpful for me to review those also.
Last year's session. So I didn't get why actually you needed the last year sessions recordings. So
Because this course is very interesting. So, apart from learning from the professor, learning it from the TA is also very helpful. Apart from viewing your presentation, I would like to see uh, the questions that the last year TA also has reviewed.
I see. Okay. So I actually do not have access to those things right now. So if
Okay,
possible, I can share. So if you can just share your email ID in the chat, something like if possible, if I get access, so I can actually provide you that.
sure,
But
sir. Okay,
yeah,
fine.
so currently I am the TA. So if you have any questions or comments, like you can always ask. I'll try
Sure,
to
sir.
answer to the
Okay,
best of my knowledge.
okay, sir.
So I am currently pursuing PhD in mechanical engineering from IIT Bombay,
Okay,
and
sir.
as a part of this Prime Minister's Research Fellowship, I got this basically opportunity to interact with all of you. Uh,
Okay,
so so I have been taking these online sessions for the last 4 weeks, and this is the fifth session. So hopefully you got the access to the sessions for the earlier week. So have you got access to those at least current for the
yes,
current?
sir. Yes, sir. I had access to them. I have seen them in the course page.
Okay. So did you find those useful?
Yes, sir.
Okay. So Mr. Kamlakar, so are you a student or a working professional?
I am neither, sir. I am currently 51 years old.
Oh,
I am not working. I stay at house, taking care of my elderly mother. So since I have good amount of time, I keep reviewing my this course details.
I see. So
I am a mechanical engineer.
you are a mechanical engineer. So have you worked
Yes.
in the industry or were you a faculty member somewhere or something else?
I worked in both. Earlier, I worked in as a mechanical engineer in finite element analysis
Okay.
field for 12 years. After that, since my mother has become old, I have switched to my native place. I
I see.
stay with her. Then I worked as a faculty in mechanical engineering college for
Okay.
4 years. After that, I stopped working and I am staying at home taking care of her.
I see. Okay. Okay. Okay, fine. So thanks, Mr. Kamlakar, for joining. So
Okay.
I think so you already have a lot of experience and knowledge in your field. So I'm not sure whether I'm making any adding any value, but I hope whatever that we are covering in this session, so it will help you also.
Sure,
Uh,
sir.
sure. So yeah, so I have got a question in the chat. An accelerometer has an undamped angular frequency of 100 hertz and a damping factor of zero point 0.6. What will be the maximum percentage overshoot? Okay. Okay, so you want to solve this also. You're getting an answer of 8% overshoot. Okay, fine. Fine. So we'll try to solve this also. Fine. Yeah, so we can take this problem, take up this problem also. So before that, like just if you can just tell me what will be the answer for the question that is in the screen. So any idea what will be the which of the statements are true in this?
For me, looks A is right.
You think A is right? Okay. Okay, fine. Anyone else? So what do we define decrement as in this context? So let us say if this is the response. So then what is the decrement here?
Initially it is x1 and then it has come to x2. So
Yeah.
maybe the ratio of x1 by x2 or x2 by x1. I'm not sure how
Yes, yes. So
decrement. Since you said decrement, it will be x2 by x1.
yes, exactly. So it will be actually x2 by x1. So it is the ratio of the second overshoot to the first overshoot, not first to
Oh,
second.
okay.
So
Oh,
that's
okay.
why
Okay. Fine.
statement number one is correct. So the percentage overshoot, it does determine the stability because it does determine how fast the system will come close to the steady state, um, and whether it actually will come to the steady state at all. Uh, and then decrement, as we just discussed, it's a ratio of second overshoot to first overshoot. And as damping ratio increases, the percentage of overshoot decreases. That is also true because for underdamped systems, so the overshoot is greater, and for overdamped systems, so there is actually no overshoot at all, or very little overshoot. So then the option B is correct. Basically, the statement number 1 and 3 is correct. So the number of oscillations are independent of damping ratio. That is not true because uh, the let us say the number of oscillations that the system makes before coming close to the steady state. So it depends on the settling time, and the settling time is dependent on the damping ratio, and so indirectly the number of oscillations are dependent on the damping ratio, not independent. So it's basically option B. Fine. So yeah, I think so we can take up your question, Venkat. So what was the question? So fine, you have been given that as an accelerometer has an undamped angular frequency of 100 hertz. So let's say omega n is 100 hertz, and it has a damping factor of zero point 0.6. So zeta is, let us say, 0.6. So what will be the maximum percentage overshoot? Okay, fine. So what is the expression for the percentage overshoot? So it's basically, so it is e to the power minus zeta pi upon square root of 1 minus zeta square. Fine, so we can calculate that. So I am getting the answer as 0.0948. So here the uh, natural frequency is not required, so it's only the damping ratio that is required. So it will be basically e to the power minus 0.6 pi upon square root of 1 minus 0.6 square. So just check whether the calculation is correct. So it's basically 9.48%. So that's what I'm getting. So is this calculation correct? Omega d is equal to omega n root of 1 minus zeta square. So that is damped natural frequency. Yes, so that using that you will get the basically just the damped natural frequency. But for this case, so yeah, using this formula you can basically write down the expression for the response. Like let us say if x of t is uh, and then using the concept of so where your omega d is omega n into root of 1 minus zeta square. So that you can use, and then using the basically, so for this we need to have some initial conditions. So if we are subjecting the system to a, let us say, some unit step, and then so for that we need to find out what is the response. So by using the initial conditions, so this is just the free vibration kind of response. So for the forced response, for a unit step input, so we need to add the the steady state response also. So that will be, let us say, some x naught, some value because of the steady state uh, value. So that so using this thing we can basically get the uh, total response, and then we have to add, so basically add the initial conditions, that let us say the displacement x is 0 at time t equal to 0, and then the derivative is also 0 at time t equal to 0. So from that we will get what is the value of the coefficients a and b, and then we can solve, basically, let us say that. So if we use the initial conditions, let us say x of 0 is 0, and and x dot 0 is also 0. And so if this x naught is also, let us say, known, so the steady state displacement value, then we can incorporate the initial conditions, and then find out what are the values of the coefficients a and b, and then we can plot the response basically. So it will
You
again look something like if this is the the step input, so then this will be something like this. So then how do we find out the overshoot? So it's this point. So this is the where the time at which the it reaches peak overshoot. So this corresponds to omega d into t is equal to pi. So it's basically has completed one half cycle. So from that we get the value of the time at which this occurs, and then we can substitute this in this. So basically x of t, where t is, so therefore t is equal to pi by omega d. So x of pi by omega d. So once we get the coefficients of like a and b, those coefficients, so then we can solve this. So this is basically x of t at t is equal to pi by omega d. So once we get the coefficients a and b, and by providing the value of this in value of pi by omega d at that time, if we evaluate that, then we will get the response x. So the x minus x naught will be the overshoot. So that as a percentage of the steady state value, so x minus x naught upon x naught. So that will be our fraction of overshoot, and this into 100. So that will be our percentage overshoot. So that is how we generally find the value of the overshoot. So right now I'm just describing the method, so you can try on your own using this approach also. It should work. So Mr. Venkat, are you satisfied with this explanation? Okay, sure. Fine. So then let us move on to our next problem. For a second order system which is subjected to a step input, so we get this kind of an equation. Uh, Now to get a damping ratio of 0.5, what should be the value of C? Now how will we solve this? Now how will we solve this problem? Now to solve this problem, what we need to do is basically just compare the coefficients of like usual second order system. So
you have the damping ratio as a C by 2 into square root of m by k.
yes,
So if we submit the values in that, I
yes,
think
yes, that is also correct. So basically, yeah. So then what is M and K?
m is 1, k is 10,
Okay.
and I think zeta equal to 0.5.
So yeah, so you're right. So basically, so we can use this same concept here. So what does the value come out to be?
Square root of 10 is some 3.33. 0.5 into
So it comes out to about 3.16, right?
3.16.
Yeah, exactly. Yeah. So we can also say that this it's basically 2 zeta omega n, and omega n square is equal to 10. So if we compare it with the standard usual form of the differential equation, so omega n is basically root 10, and then using this we'll get the same answer, basically 2 into 0.5 into square root of 10. Fine. So we can just compare the coefficient and get the answer in this question. So shall we move forward?
Okay.
Okay. Now for this system where we have been given this differential equation now, and we have to calculate rise time and peak time and the damping ratio. So again the same concept now here. We have to find out first like the damping ratio. So zeta. So it will be basically same thus C into 2 root mk.
So C is 5.
So what do we get the value for
C
zeta?
is 5. 5 over square root of 2 into square root of 10. So this is 5 into 2 slash square root of 10. Second coming 3.16.
No, it so it's basically
No, 5 by 2. Sorry. No, I'm sorry. Given 5 into 2. Stone.
0.79.
0.79.
yeah, right. So it's 0.79, and now we have to find out what is the rise time and peak time. So before that, we can also calculate what is basically omega n square. So omega n square will be 1 by 10. So omega n is 1 by root 10, and omega d will be omega n into root of 1 minus zeta square. So we can calculate basically value of omega d and omega n.
N is 1 by 1 by 4 root of 10. Omega n is a 0.31.
Yes. So omega n is 0.3162
Into
radians per second, and
square root of is equal to square root
so what do we get for omega d?
0.193.
Yes. So yes, it's 0.1936 nearly. So
of
then now let us again look at the graph of the response now. So the rise time is basically this when it crosses the steady state value for the first time, and the peak time is when it reaches the peak overshoot for the first time. So then, so let us call this as TP and this as TR. So now how do we find out what is TR and TP?
raised to
So TR occurs at the point where it just completes 1/4 of the cycle. So it corresponds to pi by 2, and TP, it corresponds to 1/2 cycle. So it corresponds to a angle of pi. So basically omega d into TR is equal to pi. So from that we can get TR, and omega d into TP. So this should be pi by 2 and this should be pi. So from this we can get what is the rise time now.
is a 1.895. TR is 1.895. Is that true?
Uh, no, how did you get 1.89?
You have given a TR is a omega t into TR equal to pi by 2.
Yes,
And omega t we have written here 0.1936.
yes.
So 0.1936 into TR equal to pi is a 3.14. Oh, sorry. I'll take it as 1 pi by 2 as 1.732. It's 3.14 by 2.
So I am getting 8.11 second.
3.14 omega 2
Yes, sir. TR is 8.1 second, TP is 16.2 seconds.
Okay.
1.71.
Yeah, I'm also getting the same thing.
Sorry for that. Okay.
So is everyone getting the same answer?
Okay. 1936. Yes, sir.
Okay. So let us move on to our next problem. So here we have been given this problem of a automobile or passenger car. So the car is going over a certain road. Now we can model the suspension as a spring and damper. So we have to find out the transfer function of the suspension system using this model. And we have to assume only the vertical displacement at the tires as the excitation of the suspension system and the vertical motion of the car body as the output. So what it basically means is, like, let us say if we model the entire car body as a single lumped mass, and let us say if we represent the suspension of all the four tires together, basically if we represent the entire suspension as a spring and damper, and then let us say we call the displacement of the tires, or basically which is exactly mirroring the road profile, so let us call that as y of t, and x of t, let us say, is the motion that is described by the it describes the motion of the mass of the car body. So now how should we go about solving this problem now? So our input is basically the road profile, which is basically y of t, and our output is the displacement of the car body, so which is x of t. So our transfer function, let us say we call it as transfer function tf, so in s domain, so that is basically the ratio of output by input, the Laplace transform of the, so that is what we have to find out. So how do we solve this problem now? So I'll give you uh, 2 minutes to think about how to solve this problem. So anyone of you got any idea on how to solve this problem? So let us now first like how to approach this problem is to first now get the differential equation of like motion equation of motion for this system in terms of x and y. So now how do we get that is by drawing the free body diagram of this mechanical system. So it's a simple mechanical system and it's a simple spring mass damper system where the base, so generally the base of the spring and damper is fixed. So here it's a movable base. So what will change is just the expressions for the spring force and damping force. That's all that would basically be different in this case. So with this, anyone has anything to say on how do we approach this? So let us draw the free body diagram of this system. So the mass is subjected to some forces. So it's basically the weight, then the spring due force and damper force. Let us call it as Fs and Fd. And the spring let us say it is being subjected to uh, so now this is our free body diagram now. Now our task is to write down the expressions for the spring force and damper force. So let us assume this time instant where let us say x is greater than y, so that the spring is basically being stretched. So then the expression for the spring force will be Fs is equal to k into x x minus y. So assuming now that x and y are measured from the equilibrium position of the system. So this is our assumption that x and y are measured from the equilibrium position. Only then we can just write that the spring force is k into x minus y. And similarly for the damper force, we can write that the relative velocity by which the piston cylinder is moving in the damper, so that will be x dot minus y dot. So now with this expressions of the spring and damper force, we can basically now write down the equation of motion for this system. Now since if the x and y are measured from their equilibrium position, so then we do not need to consider the force mg in the equation of motion. So it will be basically just mx double dot is equal to minus k into x minus y minus c into x dot minus y dot. So there is some lag in the basically the whatever that screen sharing that I'm doing and the whatever I'm speaking. So there might be some lag because of the network, Wi-Fi network that I'm using. So just please bear with that. So so if we rearrange the terms in the equation of motion now, so we will get something like this. So so this part of the left hand side part of the differential equation is the usual equation of motion of the system where in terms of x basically. So that is our output, and the terms on the right hand side basically correspond to the excitation force, or basically the force that is arising because of the variation in the load profile. So that is the force transmitted from the road through the tires to and through the suspension to the car body. So this is the transmitted force, or basically the excitation, or in other words it's basically in our current problem it's basically just the input force. So let us take the Laplace transform now for both the left hand side and right hand side now. So if we take the Laplace transform now for the both sides, then we get so Laplace transform of x dot will be basically s into x of 0, and a Laplace transform of, let us say, x double dot will be s into a Laplace transform of x dot minus x dot 0, which is basically so this is the uh, value of the Laplace transform now. So similarly, we can write the expressions for y Laplace transform of y dot and y double dot or whatever. So here we do not have y double dot, only just y dot. And if we assume that x dot 0 is also 0 and x of 0 is 0, so basically the initial conditions are 0. And y dot 0 is 0 and y of 0 is also 0, let us say. Then our Laplace transforms will be basically so if we group the terms and say that, then we will get basically the so our transfer function, let us say g of s, is the output, which is x of s, by the input y of s. So it's basically cs plus k upon ms square plus cs plus k. So this is how we can get the transfer function for this problem. So any questions or any doubts regarding this?
No, sir.
Okay. So shall we proceed? Okay, fine. So just let us look at this problem now. So it is given that there is a mercury in glass thermometer, and it has a time constant of 10 seconds. And if it is suddenly taken, uh, like basically it is now, initially it is at 20 degrees Celsius, and we suddenly put it into hot water, then what will be the temperature indicated by the thermometer after 10 seconds and 20 seconds? So that's what we have to find out. So I'll give you 2 minutes to think about this problem and we'll discuss. So anyone got any idea how we can approach this problem? Okay, so let us go step by step. So if anyone does not understand what I'm saying, just stop me and ask. Uh, so let us draw the diagram first. What for the system? So let us say if we have this kind of thermometer and it has some mercury or something, and it is immersed into some hot water. So it is at 80 degrees Celsius. So initially it was indicating 20 degrees Celsius. Now we plunge it into hot water, and it has been given that the time constant of the thermometer is 10 seconds. So for this problem, first assumption here is that the water hot water remains at 80 degrees Celsius. So let us assume that this surrounding temperature, so the our system, let us say, is the thermometer. If it is the thermometer, then this water is our surroundings. So we'll assume that our surrounding temperature around the thermometer it is fixed at 80 degrees Celsius. It is somehow maintained at 80 degrees Celsius. We will assume that. Now let us call the temperature, like let us say the T is the instantaneous or temperature indicated by the thermometer at time t, and let us say T infinity is the surrounding temperature. So we'll assume here that the surrounding temperature is constant, which is the temperature of the water. So let us call this temperature difference variable as theta of time, theta as a function of t. So from the usual law of cooling that we, law of cooling or law of heating, whatever we call it. So as we dip the thermometer, the temperature, there will be some heat transfer from the water to the thermometer, and then the mercury in the thermometer will expand, and it will like the temperature indication will gradually increase and up, and finally it will reach to the actual value of 80 degrees Celsius after some time. So how much time it will take to actually reach 80 degrees Celsius it will depend on the time constant of the thermometer. So the differential equation for the thermometer in this case will be basically d theta by dt is equal to minus some k theta. So now to solve this differential equation, so let us integrate this differential equation. So we will get d theta by theta so we will get so let us call theta naught is the temperature, this temperature difference at time t equal to 0. So then that is, so ln theta naught is basically the value of c. So then we can rewrite this as ln of theta by theta naught is equal to minus kt. So we can say that this is basically theta is equal to theta naught e to the power minus kt. So if we just rearrange the terms, we convert log into e to the power function, and we have been already given that the time constant tau is 10 seconds. So basically k is 1 by tau. So what we have is that the temperature T at time t minus T infinity is equal to e raised to minus t by tau. So this is our equation. So for Now so we know that T infinity is 80 degrees Celsius and T0 is 20 degrees Celsius. So we get basically so this is the expression for the temperature at any time t. So when t is equal to 10 seconds, it will be basically 80 minus 60 e to the power minus 1. So which is
57.9
yes. So it's about 57.9 seconds. And at
degrees Celsius.
sorry,
Sir, this is temperature, sir, degree Celsius.
yes, yes, sorry. Yes, you're right. Yes. And then at t equal to 20 seconds, it will be 80 minus 60 into e to the power minus 20 by 10. So it will be e to the power minus 2. So it will be
71.8 degrees Celsius.
okay. Yes, yes. So you're right. So it's about 71.8 degrees Celsius. So this is how we can solve this problem. So it will indicate 57.9 degrees Celsius after 10 seconds and it will indicate 71.8 at around 20 seconds. And roughly how much time do you think it will actually take to reach the actual value of 80 degrees Celsius now? Any idea?
Maybe 15 to 20 seconds. Sorry, 25 seconds.
Okay, so it's actually roughly about 5 time constants that it takes to reach nearly the steady state. So you can say it's about 50 seconds. So if we take 25 seconds, so then what it will be? It's basically 80 minus 60 into e to the power minus 2.5. So what will be that? Then it will be basically it will be about 75 degrees. And if we take 30 seconds, then so it will be about 77. So let's make a table. So let us so we got at 10 seconds it's 57.9, then at 20 seconds we got as 71.9, 71.88 whatever, and 30 seconds we get around 77, 40 seconds. So around 78.9, and at 50 seconds, $79.6. So you can see that roughly it takes about 5 time constants to reach or come close to the steady state value. So let us also calculate at 60 seconds. So it comes up to be about 79.85. So you can see how gradually, so initially the temperature rises fast, but as we go further, so the temperature rise will slow down. So let's look at another problem. So the differential equation is given now here. It's the same kind of problem that we had looked at some time ago. So we need to find out the value of the damping constant C so that the percentage overshoot is less than 9.5%. So the percentage overshoot is so for this basically we need to find out the value of zeta. So then we can say that omega n square is 4. So omega n is 2 based on the coefficients basically. So the coefficient 4 is represents omega n square, and 2 zeta omega n will be C. So zeta will be basically 2 into 2. So basically C is equal to 4 zeta. So we want the percentage overshoot to be less than 9.5%. So let us assume that 0.095. So 9.5% will be 9.5 by 100. So that is basically, so if we take the log of both sides, we will get, so here we will get a quadratic equation in terms of zeta, which we can solve to get the value of the damping ratio now. So we will get basically, so 1 minus zeta square into ln of 0.095 square is equal to pi square zeta square. And then so if we solve this equation for zeta, so we get so we get the value of damping ratio, it's around 0.6. So then we had C is equal to 4 zeta, so it will be around 2.4. So let us now look at one more problem. So when a voltage of 10 volt is applied suddenly to a moving coil voltmeter, it is observed that the pointer of the instrument rises to 11 volt before eventually settling down to the reading of 10 volt. Now we have to find out what is the damping factor and the number of oscillations that the pointer will make before it is within 0.2% of its steady state value. So now here we will assume that the voltmeter is a second order system, and it is being given a sudden input of 10 volt. So the 10 volt is a step input, and the response, so if the voltmeter indicated 0 volt earlier, and then it, let us say, starts oscillating, and then eventually it settles down to nearly 10 volt. So it is given that the first peak overshoot is about 11 volt. So then the percentage overshoot will be basically, so 11 minus 10 divided by 10 into 100, so which is 10%. So the percentage overshoot is 10%, so which is 0.1. So we can express this in terms of the damping ratio, similar to our earlier problem. And then take the log of both sides, so it will be basically minus pi zeta upon root of 1 minus zeta square is log of 0.1. And then if we square both sides and then rearrange, so we will get zeta is equal to square root of 1 plus pi square upon ln of 0.1 whole square. So we get the value of the damping ratio as comes to about 0.59. Now to find out the number of oscillations that the pointer will make before it is within 0.2% of its steady state value, so for that we need to know the settling time. So the settling time for 0.2% is steady state value is given by 4 upon zeta omega n, and the time period of oscillations, it's basically 2 pi upon omega d, which is 2 pi upon omega n into root of 1 minus zeta square. So the number of oscillations will be basically the settling time divided by the time period, so which is 4 by zeta omega n divided by 2 pi upon omega n into root of 1 minus zeta square. So it will be basically 4 by zeta omega n into omega n into root of 1 minus zeta square on 2 pi. So it will be So the number of oscillations that are completed will be 0.8685. So, so this was about the problems that we had related to the content for this week. So this is what I had for the problems for this week. So there are some more problems also which you can find in the lecture slides, so you can try them on your own. So thank you for joining this session. So we can close this session for today. Thank you very much for attending.